Using segments to find probability. Point K on segment AD is chosen at random. The probability that K is on BC is the ratio of the length of BC, this red part here, to the length of segment AD, the whole segment. And here we have the notation, the probability of K on BC, segment BC, is BC over AD. So now let's try finding the probability of these. First, the probability of K on AC, segment AC, this segment here, would be that favorable probability of that segment length AC over segment AD. Then we have the probability of K on segment AB would be this segment here, so segment AB, the favorable outcome, over the whole segment of AD. We're still talking about that segment. So we would have AB over AD and AC over AD for K. Here's another example now where we have segment ST. Point H on ST is selected at random. What is the probability that H lies on SR? So step number 1 would be to find the length of each segment. So first we need the length of SR. S is at 2 and R is at 8. So from S to R would be, from 2 to 8, would be a unit of 6. Then we have the length of ST. So from S at 2 to T at 14, we would have from 2 to 14, which would be 12. So we have a length of 6 for SR and a length of ST of 12. Step number 2 is to now find the probability. So the probability of H on SR would be the length of SR over the length of ST. We said that SR was 6 and ST was 12. So 6 over 12 would mean our probability is 1/2. That's it written as a fraction. You could also have the probability as 0.5 or 50%. Here's an example where we have segment AM. A point on AM is chosen at random. Find the probability that the point lies on the given segment. We have the given segment of JL. So that probability will be the length of JL over the whole entire segment of AM. So JL is from 9 to 11, which is a length of 2 units. That is then compared to AM, which goes from 0 to 12, which is 12 units. So we have a length of 2 over 12, or length 2 over length 12, which is the probability 2 over 12, which can simplify to 1 over 6. So their probability is 1 over 6, or we could say as a decimal is 0.17, or as a percent, we have a probability of 17% of that point being on JL. We have segment AM again, where again a point on AM is chosen at random, but now we're finding the probability that the point lies on the segment of DJ. So AM is still from 0 to 12, so we still have a length of 12. Now DJ is from 3 to 9, which is a length of 6. So we have a probability of 6 over 12, which we can reduce and simplify to 1/2. So the probability of the point being on DJ is 1/2, or 0.5, or 50%. Here we have segment AM, but now we want the probability that the point chosen at random is going to lie on the segment BE. Again, AM is a length of 12. BE, B goes from 1, E is 4, so from 1 to 4, we have a length of 3. So the probability would be the length of BE over the length of AM, so we have 3 over 12, which simplifies to 1 over 4. So it's 1/4, or 0.25, or 25%. Another example using segment AM, now we're finding the probability that the point chosen at random lies on the segment AJ. AM still has a length of 12. We're going from 0 to 12. AJ, A goes from 0 to 9, is a length of 9. So the probability would be the length of AJ over AM. So we have 9 over 12, which simplifies to 3/4. A probability of 3/4, or we could say 0.75, or 75%. Another example using segment AM, but now we want to find the probability that the point chosen at random lies on the segment CK. So we still have our total length of AM, which is 12, 0 to 12. So CK is now going from 2 to 10, which is a length of 8. So we have the probability to be the length of CK over the length of AM. So we have 8 over 12, which reduces to 2/3. So we have a probability of 2/3. Or if we want a decimal, we can round or approximate to 0.67 for 67%. Finally, let's look at the example where we're finding the probability with the segment AM that a point chosen at random lies on segment BL. AM, again, is our total length of 12. BL goes from 1 to 11, so we have a length of 10. So our probability would be the length of BL over the length of AM. So we would have 10 over 12, which reduces to 5 over 6. So 5 over 6, or if we want a decimal, 0.83, or 83%. Now here we have a completely different figure now. We have segment AC. In the figure at the right, AB over BC is equal to 1/2. What is the probability that a point chosen at random on AC will lie on BC? And explain. So since we have the ratio given to us, can we use algebraic expressions to represent this information? That's what we need to ask ourselves in order to find this probability. So if AB equals X, then BC equals 2X due to our ratio, and AC would then be a total of X plus 2X, which would give us 3X. Now we can determine the ratio to represent the probability that a point chosen at random on AC will lie on BC, can we? Well, let's use what we know about probability. We know that it would be BC over AC, so BC over the total of AC, so 2X over 3X. The X's simplify to 1 or cancel out to leave us with a probability of 2/3. A point between A and B on each number line is chosen at random. What is the probability that the point is between C and D? So in each of these examples, we're looking for the probability of the segment length CD over the segment length of AB. In each of these 4 examples, the segment length of AB is 8. We're going from 0 to 8 in all 4 cases. So the denominator for our probability will be 8. It's now just seeing the length of CD and seeing how it differs for each example to see how the probabilities change. In example A, we're going from 1 to 6, so it would be 5. You have a probability of 5 over 8. In B, CD goes from 4 to 7, which is a length of 3. So you have a probability of 3 over 8. In C, C2 goes to D6, which is a length of 4. So you have a probability of 4 over 8, which can reduce to 1/2. In D, we have C of 1 going to D of 3, which gives you a length of 2. So you have a probability of 2 over 8, which can reduce to 1/4. So you can see how all the probabilities change and compare to each other with the different lengths of CD all over the same length of AB. Here's a real-world example of using length and probability. A commuter train runs every 25 minutes. If a commuter arrives at the station at a random time, what is the probability that the commuter will have to wait no more than 5 minutes for the train? So in order to answer this question, it's best to have a visual of what this would look like with length. So which diagram models this situation best? Each number on the number line is going to represent the number of minutes remaining before the next train leaves. Well, there's a 25-minute time for the train, and the probability is waiting no more than 5 minutes. So when we're looking, DE is representing the total amount of time that the train is running, or every amount of time the train is running, that 25 minutes. So really, we're looking at CE here is looking from 5 to 25. Well, that's not the waiting time. The waiting time, we don't want to wait more than 5 minutes. So looking at C to E, that's 20 minutes. B, 0 to 5, 5 minutes, and then C, we've got 20 minutes again. So our answer here, this diagram of B, is really going to show the total of 25 minutes, and then we have the 5 minutes of the time that you don't want to be waiting for. That's your probability. Here we have the probability of DC over DE in this situation, which is going to be 5 over 25, which can reduce to 1/5 or 0.2, but would give us an answer of 20%. So there's a 20% chance that you'll be waiting no more than 5 minutes in this situation. Here's another example of using probability and length. A fitness club set up an express exercise circuit. To warm up, a person works out on the weight machines for 90 seconds. Next, the person jogs in place for 60 seconds and then takes 30 seconds to do aerobics. After this, the cycle repeats. If you enter the express circuit at a random time, what is the probability that a friend of yours is jogging in place? What is the probability that your friend would be on the weight machines? So these are two separate questions, so let's first look at jogging in place. We need to actually, that's second, because we need to look at the whole picture first. Let's draw a number line and visualize what's happening here. So we have the whole express exercise circuit. So first, you are at 0 seconds, and then you warm up, you work out on the weight machines for 90 seconds. So we'll say W is at 90. Then you jog in place for 60 seconds, so that would be, let's say J would be 90, and then 60 more seconds would be 150. And then 30 seconds you do aerobics, we'll say A, so 150, another 30 seconds would be 180. So you have a total of 180 seconds in this cycle. So that's your total length from, we'll say O for 0 seconds. We'll say O to A. Now, first we want the probability of jogging in place. So jogging in place was from 90 to 150 for a total length of that 60 seconds. So we have 60 seconds over your total of 180 seconds, so 60 over 180 is going to give us a probability of 1/3, or 33%. Then we want to look at an answer about the probability of what if they were going to be on the weight machines. So now we're looking at we're still looking at the same exercise circuit. So we're still looking from O to A. So 180 would be our total. But now we have weight machines. So the weight machines was what you started with, from 0 to 90, so 90 seconds. So 90 seconds out of that total 180 seconds, well, that would give us a probability of 1/2 or 50%. So we can kind of compare and see with the different lengths and the different probabilities, you have a higher chance of finding your friend on the weight machine with 50% chance than jogging in place. Here's a different example of probability and length. Now we have at the Space Museum Theater, a movie runs for 15 minutes. There are 5 minutes between shows. If you enter the theater at a random time, what is the probability that you will have to wait more than 2 minutes for the next movie to start? So if we visualize this situation on a number line, we start at 0, you then have 15 minutes for the movie, so we'll say M. Is that 15? 0, we'll say O. And then there's 5 minutes after that for in between shows, so we'll say B is another 5 minutes. 15 plus 5 would bring you to 20, and then you would start all over again. So we have a total amount of minutes here of 20. Now, we're trying to find the probability that you will have to wait more than 2 minutes. So let's say you waited only 2 minutes. That would be here at 2. Well, we're not looking for those 2 minutes of waiting. We're looking for the rest of the time from 2 to 20, which would be 18. So our probability would be 18 over 20, or we would have 9 over 10, which is 0.9 or 90%. That would be our probability. Lastly, let's look at this real-world example. A Sunday night sports show is on from 10 p.m. to 10:30 p.m. You want to find out if your favorite team won last weekend but forgot that the show had already started. You turn it on at 10:14 p.m. The score is announced at one random time during the show. What is the probability that you haven't missed the report about your favorite team? So if we visualize on a number line the event of this sports show, we're going from 10 to 10:30. Now you tuned in at 10:14. But if we want to find the probability that you haven't missed the report, that means the report has to be sometime between 10:14 and 10:30. So we have a total length from 10 to 10:30 of 30 minutes, and from 10:14 to 10:30 is going to be 16 minutes. So that would give us a probability of 16 over the total of 30 minutes, which we can reduce to a probability of 8 over 15. That would then either, 8 over 15 is our answer, or you can look at it as a decimal of 0.53 or 53%. So you have a little bit over half of a chance or probability that you haven't missed your report. So your odds are pretty good. You should keep watching.